I'm ready.
Okay, so thank you all for attending this final Applied PD seminar at the University of Washington. This is the final week of our quarter. The Applied PD seminar will be back, although I'm not entirely sure whether we'll go for most of the academic year or again have everything in one quarter. But it is my pleasure to introduce today's speaker, our own Ryan Creedon. Ryan obtained his PhD 2 years ago from the University of Washington, working on the asymptotic approximations to different aspects of the stability spectra of longitudinal waves in the water wave problem. And today he's going to tell us about the transverse instability of Stokes waves at finite depth. Thank you, Ryan.
Thank you so much for the introduction, Bernard, and thanks, Anastasia, as well for coordinating the technology. Fingers crossed that it holds up okay. As Bernard mentioned, today I'm going to be talking a lot about the transverse instability of Stokes waves. So what happens when you perturb these periodic water waves in a direction perpendicular to the direction of propagation instead of in a direction that's parallel to the direction of propagation. This is pretty much brand new work. We're still kind of doing the finishing touches, so to speak, on this work, but we're hoping within the next few weeks to kind of get this out. This is joint work with Hui Wind, who we heard from last week talk about the infinite depth case, and Walter Strauss, who I believe is also in the audience there. So our story starts with, of course, the Stokes waves. These are the periodic traveling wave solutions of the water wave equations. And we really like these solutions for a number of reasons, but probably the biggest reasons we care so much about them is, number one, we have ways to get asymptotic approximations to these solutions out of the Euler equations, which is very special considering how complicated those equations really are. And so that was something that George Stokes kind of gave us in 1847, at least in infinite depth. And then later on, Nekrasov, Levi-Civita, and a few others kind of worked on the finite depth case of those expansions. But then also Stokes waves are things that we can at least approximately observe in nature and in laboratory experiments. So here's a classic photo of some shallow water periodic water waves that are happening, I believe, off the coast of Panama in 1933. So it's a very classic picture of the types of waves that we're interested in. Now, unfortunately, Stokes studied these waves in the 1840s, but it really took another 120 years for people to really kind of latch on that these could be potentially interesting solutions to study. And who knows what the reasons for that could be. There might have just been other interesting physics problems to be had between those two periods. But in the 1960s, these Stokes waves kind of had a resurgence. And one of the big questions that was asked in the 1960s is whether or not these Stokes waves are stable with respect to certain types of perturbations. And so specifically in the 1960s, through the works of Lighthill and Benjamin and Fear, Whittam, Zakharov, people became very interested in what happens when you take a Stokes wave in very deep water and you perturb it longitudinally, so in the direction of the wave propagation, by a function that has nearly the same period as the underlying Stokes wave itself. And so that's kind of what you're seeing in this little representation here. In blue is your nice periodic Stokes wave, and then in red is just perturbing that Stokes wave ever so slightly by adding some sort of function that has nearly the same wave number as your Stokes wave. And so what these folks observed back in the 1960s through a combination of formal asymptotic methods and laboratory experiments was that indeed these waves appear to be unstable to these types of perturbations. And in fact, what sort of happens to the Stokes waves is they devolve into sort of a wave train that has this beat-like structure to it. So in other words, the amplitude of the waves gets modulated. And so that kind of gave rise to the modulational instability, or at least in the water waves community, we would call this the Benjamin Fear instability in honor of the laboratory experiments that Benjamin and Fear had done in the 1960s to sort of bear out this instability. Now, since the 1960s, there's been so much work related to the stability of Stokes waves, and I'm not going to claim to cover every single paper that really gives a concrete and interesting result about the stability of Stokes waves. But I do want to highlight some of the key numerical studies that sort of follow the work that was done in the 60s. And so a lot of the very first numerical stability results that we had for Stokes waves were due to Bryant and Longowit-Higgins in the 1970s. And really the focus of these papers was perturbing Stokes waves longitudinally and really just investigating the linear dynamics of the perturbations. So you're basically linearizing these Euler equations about the Stokes wave solutions. And so Bryant had kind of been the first on this to jump on this idea. And so he kind of looked at longitudinal instabilities in shallow water. And in fact, if you look at some of his later papers in the 80s, he also started to talk about the transverse instability in shallow water, which is very interesting. Not very talked about for a reason I'll get to in a second. And then Longwood-Higgins was very focused on the deep water case, which was sort of where the experiments were coming from and where the formal asymptotics at the time were sort of coming from. So that was the key results in the 70s were coming from these two gentlemen. And then we get to the 1980s, very beginning of it, with the work of McLean, which really took the results of Bryant and Longwood-Higgins and just kicked it up a whole other level. So basically, McLean was able to talk about the linear dynamics of these perturbations that you're applying to Stokes waves in water of any depth you like. And you could have any combination of a longitudinal and transverse perturbation. So it was really quite an astounding result. And in a little bit, maybe in the next 5 minutes or so, I'm actually going to give you a figure from that paper. But considering the time period that it was written in and the computing power that people had at the time, the amount of detail that he could talk about for these instabilities and their growth rates is really quite impressive. Then in the 90s, we had some work by Carif and certain collaborators of Carif, which were really starting to investigate what kind of happens in that larger amplitude limit with these transverse and longitudinal instabilities. And then finally, really the landmark result in my mind, at least, and maybe I might be a bit biased because Bernard's here in the audience, but in 2011, DeConnick and Oliveris had a paper where they, for the first time, basically computed the stability spectrum of these Stokes waves. And so essentially the stability spectrum is just a set of eigenvalues for the linearization of the Euler equations about these Stokes waves. And these eigenvalues tell you the growth rates of the perturbations that you're applying to the Stokes waves. And so McLean, Longwood-Higgins, Bryant, they all sort of talked about, these eigenvalues, and in some way they computed them. But for whatever reason, it seems like nobody decided to make a picture of what that stability spectrum looked like. And so we had to kind of wait a period of 30 years for someone to actually plot what the stability spectrum looks like. And so DeConnick and Oliveris is kind of at this point, a very classic paper that's able to show you for the first time what this stability spectrum looks like, and specifically, what are the properties of those most unstable eigenvalues? What do they look like? What do the perturbations look like, at least for short time, while the linear dynamics are still at play? And so this is a copy over on the left of what a typical stability spectrum looks like for a small amplitude Stokes wave. So everything that you saw on the previous page was, for the most part, small amplitude waves, outside of some of the work that Carif had done in the 90s. And so what we see in this stability spectrum is a number of places where eigenvalues enter the right half complex plane, and these are corresponding to the perturbations that are unstable in time. And so there's this place at the origin that has this classic figure 8 curve that we now know is due to the Benjamin Fear instability. So these are the instabilities where we're applying roughly the same sort of period as the Stokes wave to our Stokes wave. And then we have these instabilities that are further away from the origin that have these little bubbles associated with them. And those are now called the high frequency instabilities. And generally we call these high frequency instabilities just because the sort of average imaginary component is non-zero here. So the perturbations don't really have nearly the same wave number as the Stokes waves themselves. There's this non-trivial phase component to these perturbations that we're applying to our Stokes waves. And so this is kind of the picture that we had for the stability of Stokes waves about 15 years ago. And that was the state-of-the-art picture. And so in terms of rigorous stability results that are associated with this picture, there was one that actually preceded the work of DeConnick and Oliveris by quite a few years, the classic paper by Bridges and Milka. And essentially in that paper, they were able to show that there are eigenvalues that enter the right half complex plane near the origin in this stability spectrum. So if you zoom into that figure 8 and you really look at the cross that's at the origin, that's where the Bridges and Milka result kind of comes in. So they were able to detect eigenvalues that enter the right half complex plane, but they weren't able to say like the full topological aspects of those unstable eigenvalues being a figure 8 curve. But nonetheless, an extremely impressive result, very highly cited, very classic work that uses spatial dynamics to get what these unstable eigenvalues are. And then after that work, I mean, it really took quite a long time for the analysis to catch up to the numerical results. There was a paper by Wynne and Strauss that was able to take the Bridges and Milka paper and extend it to also work for infinite depth. And so their paper basically is able to get both finite and infinite depth results for getting eigenvalues near the origin that enter the right half complex plane. And so we can definitively say that we have a proof of the Benjamin-Fehr instability. This was quickly followed up by the works of Berti et al. In 2022 and 2023, where basically they proved the existence of the entire figure-8 curve, both in finite and infinite depth. An amazing result. And they always seem every year to just outdo themselves with even more impressive results that I'll get to in a second. But their first couple papers in 2022 and 2023 were focused on proving the whole entire figure-8 curve that correspond to that modulational instability. There was a work by Chen and Su in 2023 that basically followed the work of Wynne and Strauss that was able to extrapolate the linear stability results of Wynne and Strauss in infinite depth to conclude some sort of nonlinear instability results about the Benjamin-Fehr instability, which is very impressive. And to date is really the only nonlinear instability result that we really have at our disposal for these Stokes waves. And then a little bit later on in 2023, there was a paper by He and Yang that was the first to really consider what happens away from the origin with these high frequency instability bubbles. And so they managed to prove the existence of these instability bubbles, at least the first one on this imaginary axis that's closest to the origin in finite depth. Berti et al. Then followed up with that paper with another one that was able to show that, in fact, these high frequency instability bubbles exist in infinite depth as well, although you have to go higher out into the asymptotic expansions to find them. And then they just published a paper 3 weeks ago, which is extremely impressive and basically proves the existence of an infinite number of these high frequency instability bubbles on the imaginary axis. And it gives asymptotic expansions for every single one, which is just an amazing result. So in other words, we pretty much to date know everything analytically about the small amplitude stability spectrum process. But the one limitation of all these results is that they are all longitudinal results. Every single one of these papers only explores what happens when you perturb a Stokes wave in the direction of the wave propagation. And so what we want to kind of turn our attention to today is asking, well, what happens if you perturb a Stokes wave in the direction perpendicular to the direction in which the Stokes wave is propagating? And this could be paramount to a lot of very interesting dynamics. You can see in this picture here, which I've shamelessly stolen from a talk that Mariana Haragas gave at ICERM a couple of years back, but I think kind of illustrates this importance of interesting things happening in the direction transverse to these periodic water waves. It's very clear here that there is some sort of structure to these wave profiles in the perpendicular direction to the direction that these waves are actually propagating in. And so that's what we really want to explore today. We want to take these nice periodic water waves, the Stokes waves, which are traveling in this longitudinal direction, and give them a small nudge in the transverse direction by some function whose wave number is something that we can control. And then we really want to ask, okay, what wave numbers in the transverse direction are going to give rise to some sort of instability in the linear dynamics of our problem? So that's kind of the overall picture. And so I'd said about 5 minutes ago that I wanted to share a figure from McLean's paper that sort of bears out these transverse instabilities. And so here is that figure. So what you're looking at in this figure of McLean from, I believe, 1982 is where this one is taken from. What you're looking at are the various instability regions given a wave number for the longitudinal component of your perturbation and the wave number of your transverse perturbation that you're applying to Stokes waves. So here P is the longitudinal component of the perturbation, and Q on the y-axis is your transverse wave number component. And the shaded regions are corresponding to regions in this parameter space that give rise to some sort of an instability. And so basically all of the results that we know to date, excluding our own, are all happening along the x-axis here, along that p-axis, when we don't have any transverse component. And so you see a bunch of intervals that are on this axis, and they correspond to all of these different instabilities that we know about in the stability spectrum. In particular, the interval that's closest to the origin is the Benjamin-Fehr instability. So if you pick any sort of longitudinal wave number in that interval, you will get something that correlates to a Benjamin-Fehr type instability. If you go a little bit further away from the origin, you find these increasingly smaller intervals that are very, very difficult to detect numerically, but you can do it. And these intervals essentially are giving you the high frequency instability bubbles that are in that stability spectrum. What we're more interested in this paper is really what's happening on the y-axis. So you can see on the y-axis up here in purple, there seems to be an interval of transverse wave numbers that we could apply to Stokes waves and also get some type of instability. So that's what our result's going to concern. What happens in between those two cases, when you have some perturbation that has a non-trivial longitudinal component and non-trivial transverse component, is a very fascinating question. But I can tell you right now, the calculations are going to go up several orders of magnitude in difficulty. It's bad enough just going from the x-axis to the y-axis here, as you're going to see. I'm going to mask a lot of it, but you'll see some of the difficulties come in. To go off on either of these axes is quite a big jump to take, but it is possible, and we have some suspicions that a lot of what we're doing with this purely transverse instability would apply and carry over to this case when you would consider any arbitrary perturbation to your Stokes wave that has both a longitudinal and transverse component. Okay, so now what we'd like to do is kind of move away from the numerical experiments from McLean of what we already know about the transverse instability and start working towards a rigorous proof of the existence of that little tiny interval that you see on the y-axis in that previous plot. And so the way that we're going to go about this is we're going to start with a 2-pi periodic Stokes wave. So we're going to fix the period of the Stokes wave. That's easy to do. Just rescale your x to have a 2-pi periodic Stokes wave. And we're going to assume that it has a small amplitude parameter, which we're going to call epsilon. And we're going to assume we're working in finite depth here. Hui was talking about the infinite depth case last week. So now we're going to consider the complementary case of finite depth. And so here, this little x coordinate, by the way, is going to be the longitudinal coordinate in the traveling frame. So really, if you were thinking of physical coordinates, this little x is x minus ct, where c is the velocity of my Stokes waves and t is time. So you start with these Stokes waves in this traveling frame, and we're going to choose to perturb these Stokes waves in a very special way. In particular, we're going to perturb them with functions that have exponential time dependence. And this lambda parameter is going to give me the growth rate of that perturbation. And then this eta tilde is going to be a function that has the same period as the underlying Stokes waves. So this is basically ensuring that we don't have any sort of longitudinal component to our Stokes wave. In fact, the Stokes wave and the perturbation have the same period in the x direction. And then here's the thing that's going to be a little bit different about our work. We're going to incorporate this complex exponential that has some dependence on the transverse direction of the Stokes waves, which is going to be the y direction in this result. And here the role of alpha is basically going to be the transverse wave number, which is going to be the thing that for us in general is going to be non-zero. So this is very different than, for example, the papers that were done by Berti et al., where instead of having this complex exponential, they'd have something like e to the I mu x, where there'd be a longitudinal sort of component to that perturbation. And here we're getting rid of that component in favor of having the transverse component instead. So we take our Stokes waves, we perturb them in this special way, we linearize the dynamics around these Stokes waves, and eventually what you're going to wind up having to solve is a spectral problem. And the eigenvalues of this spectral problem are going to be this lambda parameter that's controlling the growth rate of the perturbations. And so now the real question is, okay, what does the operator look like that I'm trying to extract the eigenvalues of? And so in general, that operator is pretty complicated. I'm going to kind of give you a semi-explicit representation for it in a little bit, but suffice it to say that this operator is going to depend on 2 parameters. The first is, of course, the amplitude of the Stokes waves that I'm perturbing around epsilon. But then the other thing that this operator is going to depend on is the transverse frequency that I'm choosing to perturb my Stokes waves by. And in fact, it turns out that in that operator, all you ever see is this transverse wave number squared. So to cut back on some of the notation, we're just going to introduce a new parameter beta, which is going to be equal to the square of the transverse wave number. That just makes some of the expansions we have to do a little bit later on easier to work with. So we have basically a 2-parameter family of linear operators, and we want to be able to get the eigenvalues of this 2-parameter family of operators. No easy feat, but it is something that we will manage to accomplish hopefully by the end of today's talk. And so here's our main result. This is the major result of our work so far. And so I'm going to give you the informal statement first, and then I'll give you the more carefully worded statement. So in informal terms, basically what the theorem is telling you is that if you give me a Stokes wave of sufficiently small amplitude epsilon, and you work in pretty much any finite depth you want to work in, except for a few isolated depths that we can't rule out in our proof. But there is only a finite number of these isolated depths. So pretty much any depth you want, sufficiently small amplitude, I can guarantee that there exists a epsilon dependent interval for that beta parameter that you need to choose. And if you choose your beta parameter in this epsilon dependent interval, you will guarantee that that operator has an eigenvalue with positive real part. And so that will guarantee that you will have a Stokes wave that is unstable to some non-zero transverse perturbation, which kind of basically proves the thing that we're trying to look for in the works that McLean had set up in the 1980s. The more technical statement would be the following. First of all, we have to fix a depth that's not equal to this critical depth, which turns out to be about 0.25. This critical depth is special because it turns out later on in our calculations, there's a certain quantity that vanishes at this depth. And when that quantity vanishes, we don't have instability, or we can't conclude instability. But it's so long as you're not working at that one critical depth, you can then show that when epsilon is 0 and you're talking about 0 amplitude, you have a non-zero double eigenvalue of the linear operator when you plug in epsilon equals 0 into that operator. And we'll call that resonant value of my transverse wave number beta star. And if you perturb in both epsilon and beta around epsilon equals 0 and around this special resonant value, beta star of h, so here epsilon again is just taking the role of some small number, delta here is taking the role of some perturbation away from that square of my transverse wave number, then you can actually show explicitly that the corresponding eigenvalues that are sort of unstable take this form of some sort of square root type behavior in epsilon and delta, in addition to a purely imaginary term out in front. So here, t and capital delta are real analytic functions of epsilon and delta, as it turns out. And one of the things that you can show is I can always arrange it so that I can pick my delta, my little delta, so that the capital delta underneath the square root is always positive. And that's the key to giving me the instability that I'm looking for. So basically, if you choose this little delta in this very special way, which I'll explain a little bit further on in the calculations exactly where this comes from and what it means. But if you pick this delta just right, you'll be able to guarantee that this capital delta for any small epsilon is always positive. And that's what's going to give you that instability. So that's the main sort of statement of the theorem. And before I go any further, maybe I'll just pause here and ask, are there any questions before we get started with the actual outline of the proof?
Can I ask a quick question? So there's also the Phillips curve. I think that you showed it on the slide 6, right? So this remnant of the Phillips curve in the P versus Q plane.
Uh-huh.
So I think this was also found in the 60s, Phillips. Maybe it's also worthwhile to add something about that.
So these curves right here, you're saying they were also found in the 60s?
It starts from the origin, where you have the segment of the blue line, the Benjamin pair, and
Uh-huh.
then it goes in the transverse direction. So that's a part of, I mean, if you draw all 4 quadrants, it would be like a figure 8.
Yes. Yes. Oh, yeah. So I should say, so yeah, in the 60s, you're able to get this family of resonant curves that correspond to epsilon equals 0. I don't know if in the 60s, though, they actually turned on the epsilon parameter to see how these curves deformed. But you are correct. I mean, this when you set epsilon to 0, these regions collapse. The one that's corresponding to the Benjamin Fear instability is a figure 8, a figure infinity at the origin, actually. And the other one is kind of like an oval shape that sort of surrounds that figure 8 curve. So that, I think, was known in the 60s, but I don't know to what extent people turned on the epsilon parameter and asked, what do those regions look like with a non-zero epsilon?
So one other thing is that this yellow circle that you have near 1, I mean, along the horizontal axis. So where figure 8 hits the horizontal axis again, I think the growth rate of instability there is actually equal to 0. And I think it's one of the famous results of Mahara. I mean, this is actually, they were at some point trying to understand whether 2D free surface is an integrable system, and they looked at it from the standpoint of explaining the Hamiltonian in canonical variables. They looked at the matrix element associated with the four-wave interactions at those values. At that value.
Yeah, so that's fascinating. I'm not sure if I'm super familiar with that work. So if you could share that with me later, Sergey, I'd appreciate it.
I think it will be kind of interesting to understand what's the connection between these Phillips curve. I mean, the Phillips curve, you'll get it from the four-wave interactions in the Hamiltonian, and maybe it's also something that, I mean, you guys like also approach it from the standpoint of four-wave interactions, or do you just do the linearization and kind of sweep that part of the line?
Yeah, I think a natural next step forward is to kind of ask, how could I set up a perturbation expansion around this figure 8 curve that will sort of create this shaded region when I turn on epsilon, which is a very non-trivial question because the origin is a very special point in this diagram. So you have to be very careful about how you would set that up. But anyways, I'm not super familiar with how people were thinking about the resonant curves and how they were changing with epsilon in the 60s. So if you want to share some things afterwards, that'd be great.
Sure, cool.
I have a quick question as well. So for this big theorem, is lambda 0 purely imaginary?
Yes, yes. So when epsilon is equal to 0, you find that all of your eigenvalues are on the imaginary axis. So you don't have any instability of flat water.
Yeah.
Any other questions? Okay, if not, let's go ahead and dive right into a rough proof sketch. Let's see, how am I doing on time? So my goal is maybe 20 minutes of this, which we'll see how we do. So before I give you the proof sketch, let me just give you a little picture that sort of corresponds with the statement of the theorem. I actually forgot that I had this slide in here, but it's a pretty important one, so shame on me for forgetting this. So before I give you the promised proof, let me just give you a picture of that sort of summarizes or encapsulates this main result. So I told you that you have to pick this delta parameter just right to be able to get these unstable eigenvalues. And it turns out that what you're seeing here for this particular choice of delta is very roughly an expansion for that delta parameter as a function of epsilon. And so it turns out that what you can do is you can plug that expansion of delta as a function of epsilon into your expression for these eigenvalues, and you can get an asymptotic expansion for the unstable eigenvalues. And it turns out when you do that, you'll find that these unstable eigenvalues have to lie on an ellipse, or something approximate to an ellipse, which is exactly what we see in the longitudinal stability spectrum for the high frequency instabilities. But again, I remind you, we're not talking about the longitudinal spectrum here, we're talking about the transverse spectrum. And so one of the things that you can do is you can plot what these asymptotic approximations to the eigenvalues are, and you can plot them against numerical computations using like a totally different independent method. And so what you're seeing in these three plots are those unstable eigenvalues. The orange curves are the asymptotic predictions, and the blue dots are the numerical computations of the unstable eigenvalues. The first figure is for depth h equals 1, second is h equals 3/2, and third is h equals 2. So we have a lot of confidence that this result is accurate, and vice versa, that all the numerical computations that people have been doing are really capturing the behavior that we're supposed to be looking at. So in other words, all the numerical analysts and all of the rigorous analysts have been kind of speaking the same language, maybe using different notation, but everything is consistent with each other. So really what we're after are these unstable eigenvalues that are on these approximate ellipses in the transverse stability spectrum.
Ryan,
oh, sorry, go ahead, Bernard.
So what happens if so your prediction for your critical depth case is 0.25.
Mm-hmm.
No asymptotic curve, at least not to the order that you're going.
Yes.
What does the numeric show?
So the numerics unfortunately show me nothing because the size of the bubble starts to get so small that I get close to the error of the Floquet-Fourier-Hill method, and then I can't quite see it.
So you just need to go quadruple precision or something, or?
Yeah, something like that. Yeah.
Okay.
Yeah, ideally. I'd really love to. I had the same problem with the high frequency instability bubble as well in that one critical depth that we found in our paper. Similar problem. You run right up against where that round off error is.
Thank you.
Yep. Great question. All right, now for the much promised proof sketch. I'm going to go through this relatively quickly because, as you can imagine, a lot of the calculations involved in the finite depth problem are very painful, and you almost have to right away go over to Mathematica to help you because doing it by hand is insanity. But here's the starting point. So, of course, we have to start with Euler's equations that govern the behavior of these water waves. Here we're going to be working in a domain with 3 independent spatial variables. X will be the longitudinal direction, Y the transverse direction, Z is going to be my depth direction, and we're working with a Z coordinate that's below my free surface eta and above the constant depth of this fluid, which will be minus H. So here H we're going to take to be a positive number that represents the depth. And so here are the much loved Euler equations. You've all seen them probably many times before in this seminar, so I'm not going to belabor the point too much about them. Phi here is representing the velocity potential in the bulk of my fluid, so in this domain d of t, and eta is representing, again, the evolution of that free surface at the top of my water. Now, this formulation, written in terms of the Laplace equation with a bunch of boundary conditions, can be helpful for certain things, but for our purposes, really all we care about is what's happening at the free surface and what the velocity potential at the free surface is. So we immediately switch over to the Zakharov-Craig-Sulem formulation of the water wave problem. And so that's kind of the starting point of all of our analysis, is to flip over to that formulation of the water wave problem. And then at this point, you then have a few steps that you have to do before you arrive at your spectral stability problem. And again, Hui did a really wonderful job of kind of walking you through the basic idea of how this works. So I'm going to exploit the fact that he gave a talk on this last week and kind of gloss over all of these details. But the idea is you're going to linearize this Zakharov-Craig-Sulem formulation in a traveling frame about these Stokes waves. And so now you're going to have some sort of linear Euler equations written in this Zakharov-Craig-Sulem formulation. You're going to notice in that formulation that there are a lot of calls to the Dirichlet to Neumann operator, which is basically mapping the Dirichlet conditions of the velocity potential to the normal derivative of the velocity potential at that free surface. And that's a very nasty operator to work with. So any chance you have to eliminate some of the calls to that operator, it's a good thing to do. And so one of the ways that you can do that is introducing these good unknowns of Al and Haq, which basically allows you to eliminate some of these unnecessary calls to the Dirichlet to Neumann operator. And so basically, when you're done with this step, there's only one call to the Dirichlet to Neumann operator in that linear problem, which is very, very nice. And hence why they call it the good unknowns. And then the last thing that you have to do is a conformal transformation to basically flatten the domain of the Stokes waves. And so in this case, we're going to be flattening our domain to be 2 pi periodic in the x direction. And then because this is a finite depth problem, we're not going to have like a semi-infinite strip like you'd have in infinite depth. Here, we're going to have some sort of rectangular domain that's bounded in that z direction when we do that conformal transformation. So all of this stuff, if you're really interested in it, you can read the paper by Wynn and Strauss. You could also read the papers by Berti et al. Both of them have excellent write-ups for this what I would consider classic setup at this point for how you get to this spectral problem. I'm going to just move ahead and just tell you this is what the spectral problem ends up looking like. So here, this operator L sub epsilon beta, this is the operator that you want to find the eigenvalues of to be able to determine whether or not your Stokes waves are transversely unstable. And so in general, this operator, L epsilon beta, 3 of the 4 entries in this matrix operator equation are super nice, super local. They're basically just derivatives and then possibly multiplications by some functions which are real analytic and epsilon. And these functions are real analytic and epsilon because they basically inherit the real analyticity of the Stokes wave expansions in that epsilon parameter. And so you can explicitly compute these expansions to whatever order you want. For our purposes, you're going to have to go out to at least 3rd order to be able to compute the instability that we're looking for. So that in and of itself is a bit of a chore, but you can do it. And so the p epsilon and the q epsilon here are super explicit and super well understood. And you can find their expansions both in our papers or the Berti et al. Papers or the Wynn and Strauss paper from 2022. So there's lots of places you can get them. The other entry that's in this operator L epsilon beta is the remnants of your Dirichlet-Neumann operator. But now it's your Dirichlet-Neumann operator in this sort of conformal variables instead of just being in physical variables. And in general, that operator is still pretty complicated. The way that you want to think about this operator is you give me some function of x, and basically what you have to go off and compute is the solution of this elliptic problem for capital theta. And f of x is representing the Dirichlet conditions of that elliptic problem at the top surface of this rectangle. And so you have to go off and solve that elliptic problem. And then once you're done solving that elliptic problem, then you have to take the normal derivative at that top interface. So you have to take that z derivative and then evaluate that at z equals 0. So you're basically getting the trace of that normal derivative at that top interface. And that would be what this operator returns to you. It's not a super friendly function, not a super friendly operator, at least when you first look at it like this. And what makes things worse than infinite depth is this bottom boundary condition. When you look at this bottom boundary condition, we have to evaluate the normal derivative of this capital theta at this bottom boundary. But unfortunately, what happens is when you do the conformal transformation, and Sergey, you're probably intimately familiar with this, when you do this conformal transformation, unfortunately, your physical depth changes into something that's now an epsilon dependent depth. So you have this bottom boundary condition that unfortunately involves epsilon in it. And so you have two options at this point for your analysis. Either you suck it up and you keep the epsilon in that bottom boundary condition, but then your function spaces are going to be epsilon dependent function spaces, which is kind of hard to think about exactly. Or you could do what we did, which is to rescale the z variable so the epsilon dependence drops out of the bottom boundary condition. Unfortunately, the cost of that is you're going to get a few more terms in your partial differential equation that are epsilon dependent. And it's those extra terms that require a lot of tender love and care to actually prove the following statements about the Dirichlet-Neumann operator, which in the interest of time, I'm going to skip over the proof of this statement because it's quite involved and slightly above my pay grade. But here are the results nonetheless that you can prove about that Dirichlet-Neumann operator. For any finite depth and any sufficiently small epsilon and any beta parameter greater than 0, forget about the resonant beta values for now, just any beta value you want, you can show that this operator is a bounded linear operator over the function space that we really want to be working over for this problem, which is basically the Sobolev space H1 for x values between minus pi and pi. We know that this operator is self-adjoint over L2, basically. We know, and this is the most important thing that we know, that this operator is locally real analytic in epsilon and beta, which basically means I can represent this Dirichlet-Neumann operator as a Taylor series expansion around epsilon equals 0 and around any beta value that I want. That's the thing that we're going to exploit the most. And then lastly, we know exactly what this Dirichlet-Neumann operator does when epsilon is exactly 0. In that case, the Dirichlet-Neumann operator is a Fourier multiplier operator, and here's the symbol for that Fourier multiplier operator. And if you go back to the work of Berti et al. 2 years ago, you'll see that their Fourier multiplier operator is here, but it's been modified by the addition of these beta parameters that are inside these square roots. So it's very similar to what was already known in the longitudinal case, but just ever so slightly different. And that transverse direction really makes the calculations involved a lot harder. So these are some of the things that we know about that Dirichlet-Neumann operator. And as a result, the main sort of takeaway from this result is that we can now take our operator L epsilon beta, and we can start thinking about what happens when you expand that operator around epsilon equals 0, and you expand that operator around beta equals that resonant value of beta that we see in the epsilon equals 0 stability spectrum. So that's going to be the hallmark thing. So this is where the analysis is probably at its peak in the proof. And now everything that follows is going to be tedious expansions, now that we know that we can actually do the expansions. So we start with the easy stuff. We start when epsilon is exactly equal to 0, in which case that Dirichlet-Neumann operator becomes a Fourier multiplier operator with, okay, maybe not the world's greatest symbol, but it's still explicit. And so we can actually calculate what the eigenvalues are for that operator. And as I mentioned before, they all end up being purely imaginary. And so flat water is spectrally stable to the surprise of nobody. And now what we're going to do is we're going to try to extract what are those resonant beta values. What are those values that correspond to double eigenvalues in this stability spectrum? Because we know from McKay and Safman that when we turn on epsilon at these double eigenvalues, there's a tendency, perhaps, for those eigenvalues to split off the imaginary axis when we turn on epsilon. So we're looking for these double eigenvalues. And so we get a complicated transcendental equation for beta star. And there's a lot of different resonant values that we could pick for this beta star. We're actually going for the simplest one that McLean mentions in his work, which is when this parameter m, this integer m, is equal to 1. So here the role of this integer m is basically like the difference in the wave numbers between your two eigenfunctions that are corresponding to this double eigenvalue. And so the simplest possible arrangement you can have is when the difference between those wave numbers is basically 1. And so that's what we're opting for here. So in other words, this is going to restrict us at this point to talking about the transverse instability bubble that's closest to the origin. That's basically what we're doing by choosing this restriction. Luckily for us, this is the transverse instability bubble that's usually the largest for sufficiently small epsilon. So we're still going to get the result that we're looking for, specifically for the largest transverse instability. Okay, so now what does this beta star look like as a function of h? Well, in general, I said it's a solution of some complicated transcendental function of h. But what we do know about this beta star is that it is real analytic in h. So you can do a Taylor series expansion along any point in this profile. And in particular, we know what the limiting behavior of this beta star of h looks like as h goes to 0 and as h goes to infinity. And in particular, as h goes to 0, beta star of h looks approximately like a quadratic. And as h goes to infinity, beta star of h looks like a decaying exponential that's getting close to a limiting value that I'm calling beta star infinity. And that beta star infinity is exactly the resonant beta value that Hui mentioned in infinite depth last week. So in fact, this limit as h goes to infinity is a very well-defined limit for the transverse instability. That's not the case for the Benjamin-Fehr instability, but here we get a little bit lucky. This is a well-defined limit, so everything as h goes to infinity is consistent with Hui's results from last week, which is very, very nice. And so this is what beta star looks like as a function of h. Once you have pretty much everything known about your eigenvalues, everything known about those resonant values of your eigenvalues, those double eigenvalues, you can run off and explicitly calculate what the eigenfunctions are. There are two of them in this case because we have a double eigenvalue, which has geometric and algebraic multiplicity of 2. So you can get explicit expressions for those. And now this is the part where Kato's similarity transformation comes in, which is basically a special mapping that allows you to take information about your eigenfunctions when epsilon is equal to 0 and calculate explicitly what your eigenfunctions are going to look like when epsilon is non-zero. And in fact, we can go one step further and not just consider what happens to our eigenfunctions when we turn on epsilon, but what happens when we perturb our beta parameter around the resonant beta parameter as well. So this explicit mapping is basically giving us a Rosetta Stone that connects what's happening when epsilon is 0 at this resonant beta value to what's happening in a neighborhood of epsilon equals 0 and a neighborhood of that resonant value for these eigenfunctions. Here, the capital P's that you see is the standard projection operator that you would get, the spectral projection operator that you would get from resolvent theory, essentially. So it's a super explicit map up to being able to calculate this contour integral in the complex plane. But again, we're not going to end up doing that. Instead, we're going to be expanding all of this stuff around epsilon equals 0 and around my beta star value, essentially. Okay, and so this is just explicitly kind of giving you that connection between the eigenfunctions themselves and the eigenfunctions when epsilon and delta are non-zero. So at this point, we can basically conclude that my eigenfunctions are going to be real analytic in epsilon and delta because this Kato similarity transformation is real analytic in epsilon and delta, because this function that I wrote down is real analytic, and also this projection operator is real analytic in epsilon and delta. So at this Hi, folks. Sorry for that interruption there. It seems like my internet decided to go out at the worst possible time. Now, I'm told that I was left off somewhere towards the end of step 5, but I figured I'd go maybe one slide before that just for continuity's sake. And that way we're all on the same page with where we were before I got kicked off. So, as I was saying, towards the end of this 4th step, you basically now have the eigenfunctions not just at epsilon equals 0 and at your resonant value beta star, but now you're able to basically calculate what your eigenfunctions are when epsilon is non-zero and when you're perturbing around your resonant value beta star. And so that would be given by this formula right here. And now, sort of moving on to the next step here, step 5, you're going to take these eigenfunctions and you're going to use them to project onto the domain and range of this operator with the non-zero epsilon and the non-zero delta. And when you do this projection step, you're going to be left with no longer an infinite dimensional spectral problem, but you're going to be left with a 2 by 2 matrix eigenvalue problem. And here, the coefficients that you're seeing inside of this matrix, the capital A, the capital B, and the capital C, these are all real valued, real analytic functions, not only of epsilon, not only of delta, but also on your depth parameter h. And so now what we're going to do is we're going to take this 2 by 2 matrix and we're going to calculate its eigenvalues explicitly, which is just an application of the quadratic formula. And we're going to find that our eigenvalues look like lambda naught, which is some purely imaginary eigenvalue, plus a purely imaginary correction that's in the form of I times capital T. So here capital T is a real analytic function of epsilon and delta. In fact, it's the trace of this second matrix that you see up here. And then we'll have plus or minus the square root of this delta function, this capital delta function that is, and this capital delta function is also a real analytic function of epsilon and delta. Now what we want to do, now that we have these explicit representations for these eigenvalues, is we want to pick little delta underneath this square root to make sure that capital delta underneath that square root is positive for all sufficiently small epsilon. So that's going to be our next goal. And so in order to do this, we're going to need expansions for capital delta as a function of epsilon and delta. And in order to get expansions for capital delta, we're going to need expansions for capital A, capital B, and capital C. And in order to get expansions for capital A, capital B, and capital C, we need expansions for our eigenfunctions, which means we need to expand the Kato similarity transformation, which means we need to expand the spectral projection operator, which means we need to expand the Dirichlet-Neumann operator. There's many, many, many things that we have to expand now. And so this becomes a real tour de force of expansions, a real Russian doll, nested doll of expansions that we have to do in order to calculate the expansion of capital delta. But it turns out that we can do that. And more specifically, for the functions capital A, capital B, and capital C that capital delta function depends on, here are the explicit expansions. Up to, I think, 4th order in capital A and capital C, and 3rd order in capital B. Now, it turns out that every single one of these coefficients that you see in these expansions, the little a's, little b's, and little c's, these are all explicitly known functions that depend on the depth as well as on the resonant value beta star, which implicitly also depends on h. So really, these coefficients at the end of the day are real analytic functions of the depth parameter. That's all that remains in these coefficients. And so what we're going to do next is basically go back to our problem of trying to make capital delta positive. And the way that we're going to do that is by taking these expansions for A, B, and C and plugging them into the definition of what capital delta is. And we're going to get a real ugly looking expansion in both the epsilon and the delta variables. And what we're trying to do is use method of dominant balance to figure out how to pick little delta to make sure that capital delta is always positive for sufficiently small epsilon. And if you allow yourself to use something like the method of dominant balance to find that right scaling, you'll find that your little delta ends up scaling like epsilon squared, with this particular prefactor in front of the epsilon squared. So this epsilon squared is basically this coefficient is chosen to knock out some of the lower order terms that are in that expansion. And then what remains is going to be a third order term where this theta parameter is basically like the new delta parameter. So essentially what we're doing in this step is we're renormalizing this delta parameter. We're sending delta now to theta, where theta is this coefficient in front of the cubic term in this sort of expansion. If you plug in this particular choice for delta into our capital delta function, you will get the following expansion for capital delta. And here's the important thing to notice. The first term that survives in this expansion of capital delta is something that's epsilon to the sixth, and the coefficient in front of that epsilon to the sixth term depends on theta. It depends on this parameter theta. And so now at this point, what I'm going to do is I'm going to choose this theta parameter to guarantee that this coefficient in front of epsilon to the sixth power is positive. And so basically this gets me this interval of theta values that are bounded between this number, kappa 1 and minus kappa 1, that I need to pick in order to guarantee that capital delta is positive for sufficiently small epsilon. And so this is basically the end of the proof. This is the result that we want. We're going to choose this little delta. And what we've just demonstrated is if when we choose this theta parameter to be in this interval of values, we are going to get a capital delta that's positive, and therefore we're going to get a positive real part to our eigenvalues. And that's going to give me the transverse instability. But we can't do this so quickly because one of the things, actually two of the things that can go wrong here is that if A01 and C01 are equal to each other for all depths h, we're going to be toast because we'd be dividing by 0 here in this expression for kappa 1. So we have to make sure that doesn't happen. And we also have to make sure that this numerator, B30, also doesn't identically vanish with our depth parameter h. Because if it does, then I don't really have an interval of theta values here that's going to make this work. I'm going to be stuck with a negative underneath that square root, which is going to give me a purely imaginary correction of my eigenvalues. So we really do need to check the following two facts about these coefficients. And so the first fact that A01 is not equal to C01 is pretty easy to check. We have explicit expressions for what A01 is and what C01 is. And from those explicit expressions, you can show right away that they have opposite signs. So they can't be equal to each other. So that takes care of the first condition we need. The second condition we need is a little bit more difficult to show, and that is that B30 is not identically 0. One of the first things that you can do with this B30 is you can just plot the function. And so here's what B30 looks like as a function of h. And from this, you can clearly see that for pretty much all values of h, B30 is not 0. And so for pretty much all values of h, we're going to be able to conclude that the transverse instability exists. It's obvious, though, that there's one spot right about here when h is about 0.25 when B30 is going to be 0. And so for that one special critical depth, we are not going to be able to conclude the transverse instability. Now, all of this is sort of a proof by picture. If you want to make this rigorous, one of the things that you can explicitly show is what the limiting behavior of this B30 coefficient is as a function of h. Specifically, you can show that B30 looks like h to the minus 9/2 power as h goes to 0 plus. So that's guaranteeing that for sufficiently small h, B30 is not going to be 0. And another thing that you can show is in the limit as h goes to infinity, B30 goes to a real number, which we're going to call B30 infinity, and that real number is negative. So for sufficiently large h, we know that B30 is not 0. And in fact, there's this powerful theorem called the identity theorem from complex analysis and also from studying real analytic functions of an independent variable over some open domain that tells you that, in fact, these real analytic functions can only have a finite number of isolated depths for which they are equal to 0. So, in fact, what we can prove rigorously is that for almost every single depth h, B30 is not 0. There's only going to be a handful of finite number of isolated depths where B30 vanishes. And according to the intermediate value theorem, we have at least one of these. And that one happens to be that critical value of 0.25. So that's as much as we can sort of surmise analytically that's true about this picture. There's going to be a finite number of depths for which this B30 vanishes. And in fact, for this problem, there's only one, and it happens right here at about 0.25. For all other depths, you don't have to worry about B30 vanishing. And so this allows me to sort of wrap up our tour of these unstable eigenvalues of this 2x2 matrix. So pick any depth that's not equal to this critical depth where B30 vanishes. Choose your little delta parameter in this way that we've already discussed, and that will guarantee that capital delta will be positive. So that means that I will have an unstable eigenvalue here because underneath this square root, I will have a positive number. So there'll be a real part correction here. And in fact, if you really wanted to, we could now get expansions for what these eigenvalues look like in terms of their real and imaginary parts. And we see that the real part of these eigenvalues go like epsilon cubed. And the imaginary part, first of all, looks like the imaginary part of my unperturbed eigenvalue plus a second order correction plus a third order correction, as it turns out. And so this is basically the conclusion of the proof. We've demonstrated that, in fact, if we choose our beta parameter to be equal to beta star plus delta, where delta is given by this quadratic in epsilon plus this cubic in epsilon, then we will get eigenvalues with positive real part, and we have expansions for the real and imaginary parts of these eigenvalues. And if you want to eliminate the theta parameter from the real and imaginary parts of these eigenvalues, which right now is sort of taking the role as parameterizing this curve of unstable eigenvalues, if you eliminate that parameter theta from the real and imaginary parts, you can very quickly show that, in fact, these unstable eigenvalues lie approximately on an ellipse. The semi-major and semi-minor axes of this ellipse are order epsilon cubed, which is consistent with the fact that that most unstable real part of my eigenvalue looks like epsilon cubed. And the center of this ellipse is centered on the imaginary axis and drifts away from the epsilon equals 0 unstable eigenvalue, or I shouldn't say unstable eigenvalue, excuse me, the double eigenvalue when epsilon is 0. This drifts like epsilon squared away from that double eigenvalue. And in fact, these ellipses are exactly what I plotted at the beginning of this talk. And as we saw before, they match perfectly with numerical computations. So let's wrap this up. Here's the major conclusions here. This is the first ever proof of a 3D instability of a Stokes wave in finite depth. So here we are considering a perturbation where we have to look at the entire two-dimensional free surface of a fully three-dimensional wave. And so who we had talked about last week, what to do in infinite depth, this is now the proof that takes care of all the other cases when you have a finite depth fluid. We've also shown that this very first type 2 transverse instability grows like order epsilon cubed. And if you go back to the work of McLean, you can kind of see that this was already known numerically. And now it's nice to know that we now have that rigorously as well. And to sort of put a reference frame here, in finite depth, the Benjamin Fear instability grows like order epsilon squared. The first high frequency instability bubble goes like order epsilon squared. So this transverse instability is something that's an order of magnitude smaller in finite depth. In infinite depth, it turns out that this transverse instability remains order epsilon cubed, while that first high frequency instability becomes order epsilon to the fourth. So the transverse instability dominates the high frequency instabilities in infinite depth. But in finite depth, it's the other way around. The other thing that we've shown now is essentially that this proof seems to give us an isola, a bubble of unstable eigenvalues in our transverse stability spectrum, basically for any depth we like, except for that one critical depth where that B30 quantity vanishes, in which case you have to do a higher order calculation to figure out whether you're going to have instability at that particular depth. We suspect that this proof also works if our perturbations had both a longitudinal and a transverse component, although as I said at the beginning of today's talk, that kind of ups the difficulty level quite a lot when you're having to keep track of both longitudinal and transverse components. But it's something that we are thinking about. And if you'd like to discuss a little bit more in depth, maybe in person, I know Walter and myself will definitely be at NWCS, and we'd be happy to talk more in person. Thank you so much for your attention, and I do apologize again for that cutoff that happened during the actual talk.